They say they fixed AI's memory. That's a bold claim, right? A statement so audacious it makes you stop what you're doing. You hear that and you lean in, because you know the struggle. If you've ever used an AI, you've felt that strange mix of awe and frustration. It's brilliant 1 second, composing a flawless email or a complex piece of code, and then just moments later it completely forgets what you just told it. You ask a follow-up question, and it's like you're starting the conversation all over again. It's like talking to a goldfish, except this goldfish can write poetry and has access to the entire internet. This isn't a small bug. It's a fundamental, crippling limitation we call AI amnesia. And it gets worse as the models get bigger. Trillion parameter models get lost in their own thoughts, drowning in a sea of data. They become unable to follow a long chain of reasoning. They start strong, then lose the plot, their logic fraying at the edges. Think about the irony. We built these incredible machines, vast digital cathedrals holding the world's knowledge, but they forget what they thought just 10 steps ago. That paradox is a massive roadblock, preventing AI from tackling truly complex, multi-stage problems. Imagine trying to solve a 50-step logic problem. By step 48, your own brain is probably melting under the cognitive load. Humans and our current digital minds share this exact limit. Working memory maxes out. For AI, this has been an unbreakable ceiling. Until, perhaps, now. Out of nowhere, a company called Kimi AI quietly published a paper titled Attention Residuals. It didn't come with a flashy product launch or a big press tour. It was just a technical document. But inside, it might just hold the cure for AI amnesia. Deep networks are literally many layers, like floors in a skyscraper. Hundreds, sometimes thousands of layers. Each layer transforms and passes information onward. By layer 120, thinking gets very abstract. Residual connections fix training by adding a highway for information. Signals could flow without fading, unlocking deep learning. But the fix kept adding everything into one growing pile. Early details get buried. Picture 50 chefs, each adding to one pot. First chef adds delicate basil, the original prompt. Then gallons of broth, sacks of potatoes, crates of tomatoes. By chef 50, it's an overflowing mess. Can you still taste the basil? Almost zero. Later layers must shout huge signals to be noticed. The system becomes unbalanced, inefficient, and forgetful. Root cause? One blended signal buries early info. Before transformers, the dominant models were recurrent neural networks, or RNNs. They processed text sequentially, word by word, trying to hold on to the entire context in a single, constantly updated memory state. But this created a bottleneck. As the text got longer, older information was inevitably overwritten or diluted, causing the model to forget crucial details from the beginning of a long document. The attention mechanism was a breakthrough. It gave models the ability to create direct shortcuts, allowing them to look back across the entire input sequence at any time and pick out exactly what's relevant for the current word they're processing. Suddenly, context became crystal clear. A pronoun like it could be directly linked to the noun it referred to, even if it was many sentences away. The researchers at Kimi saw a fascinating parallel. A model's depth, its stack of processing layers, is like a long sentence. Information passed from layer to layer gets transformed and can lose its original fidelity. Just like an RNN forgets the start of a long text. So they applied the same logic. They gave the layers themselves attention, a technique they called attention residuals. Now each layer can ask a direct question. What specific information do I need from earlier layers to do my job better? It sends out a query and compares it to the keys of all previous layers, pulling the most relevant values directly. The messy, overprocessed information from the immediately preceding layer becomes a buffet of clean, original choices from the entire model depth. A later layer can decide to take more of what's useful and less of what's not. It can reach all the way back to an early layer to retrieve the basil when it's needed for the final dish. But there's a massive practical problem. At the scale of models like GPT-4, the model is so large it has to live across thousands of GPUs in a data center. Allowing every single layer to talk to every other layer would cause an explosion of network traffic between all these chips. The GPUs would sit idle, waiting on data to cross the wires. It's simply too slow and far too costly. The elegant fix is block attention residuals. The model is divided into blocks of layers that live together on the same physical hardware. Inside each block, Layers can freely use the attention buffet, selecting information from each other with lightning speed. But between the blocks, they only send a single, compressed representative summary. This drastically cuts down on network traffic, making the whole system efficient and scalable. It's the best of both worlds, the profound reasoning power of deep, interconnected layers, combined with a design that respects the physical realities of modern supercomputers. So, after all the theory, the big question remains: does it actually work? The answer is a resounding yes, and the results are impressive on multiple fronts. First, let's talk efficiency. For the same level of performance as a standard model, a network using attention residuals requires 1.25x less compute to train. That might not sound like much, but it's a huge leap in efficiency. At the massive scale of frontier model training, that efficiency translates directly into millions of dollars saved. For AI labs, this means they can either pocket those savings or, more likely, reinvest them to build even more capable models for the same budget. But it's not just about saving money. The real prize is performance. On notoriously tough reasoning benchmarks like GPQA Diamond, a test designed to stump even graduate-level experts, models with this architecture see their scores jump by a massive 7.5 points. We also see significant gains on other key benchmarks like MMLU, and across difficult math and coding tasks. This isn't just about pattern matching. The model can now hold the initial premise of a complex problem, follow a long series of logical steps, and reliably land the correct answer. Under the hood, the reason for this is clear. Signals stay bounded and healthy, no more burying crucial information from the early layers under an avalanche of later processing. Instead, learning signals distribute evenly across the entire network. Every part of the model contributes effectively, making the whole system healthier and more stable. With attention residuals, going deeper just keeps helping. Unlike older architectures that hit a point of diminishing returns, these models continue to improve as more layers are added. This means models can think in much longer, more coherent chains without losing the thread. This is a game changer for complex, long-chain tasks, like planning scientific experiments or executing multi-step agent workflows. When we look inside, we see fascinating patterns emerge. The network exhibits both locality, where adjacent layers communicate, and sudden long-range jumps, where a late layer might directly query an early one. It behaves almost like a biological brain. The network dynamically rewires itself, adapting its internal communication pathways for each specific task. It's no longer a static, rigid architecture. It's adaptive. Ultimately, better memory unlocks better reasoning. This fundamental improvement has the potential to accelerate progress across every field, from science and medicine to engineering and art. Industry leaders like Jensen Huang at NVIDIA, whose hardware powers this revolution, know the stakes are incredibly high. The major AI labs, OpenAI, Google, Anthropic, xAI, are all in a fierce race to solve fundamental challenges just like this one. An architectural breakthrough can provide a decisive edge. Of course, powerful new ideas need careful and rigorous testing. As we push the boundaries of capability, we must always keep the crucial issues of cost, safety, and auditability firmly in mind.